system. And then what else did we learn so far? Parametric. Now we're going to learn about polar. Excellent, polar. Okay. So the idea here is that you still need two pieces of information. The first piece of information you need is degree rotation from the positive x-axis. And the second piece of information you need is the distance from the origin. Any point, as long as you've specified an origin, you can locate any point in space using this method. So the idea is, instead of xy, you are going to have r theta. You're going to have the distance the point is from the origin, and then theta, which is this degree angle right there. The angle measure from the positive x-axis to the line segment you would get if you connected the origin to the point. So for example, let's do this, check this point U out right there. Cartesian coordinates, what point would that be in Cartesian coordinates right there?
3, 4.
Looks like it's 3, 4. So if we wanted to find that point in polar form, first would be the r value, which would be the length of that segment. What is the length of that segment, Henry?
It is 3 squared plus
4 squared, all square rooted, which is 5. In this case, it's 5. You would next need theta. There are many different ways you could go about getting theta right here. What's one way you could get theta? What's one trig function you could use to get theta? You could use tangent. You know that tangent of theta is going to be equal to 4 over 3 is going to be equal to 4 over 3. So if we wanted to find theta, what would we need? We need arctangent. So we'd say that theta is equal to tan inverse of 4 over 3. So is that a nice value? No, it's not a nice value. It's not. It could be worse, I guess. But generally speaking, though, what angle? It would be tan inverse of 4/3. What would you need? Your calculator, unless maybe you've memorized that. I don't think you have, but have you?
Well, isn't it 3, 4, 5 triangle going to be pi 3?
No, it's not. 3, 4, 5 triangle is like 58 point something. No, it's not. Yeah, boo. Point being, it's still two pieces of information. It's still two pieces of information. Let's get more general, though. Let's say we had this point P and we didn't know the exact value. Let's just call it xy. Let's call it xy. What's the r value going to be? What's the distance xy is from the origin? What's that distance? Someone tell me. Just tell me. What is it? Henry, tell me what it is.
X squared plus y squared.
Yep. Correct. There's your r value right there. Is the square root of x squared plus y squared. What about the theta value? What about the theta value? What could you say? You could call it, there's several ways to do it. What's one way? Yep. Inverse tangent of y over x. You absolutely could do that right there. And there's a general conversion. This right here is going from Cartesian to polar. Cartesian to polar. So let's say, hold on a sec. Let's say we did. So what is U going to be? 5, tan inverse of 4 over 3. Absolutely. What about V? Who has V for me? Jesse. 5, pi. Is that correct?
No.
0, -5. You're going to have to go all the way around and down. Pi plus pi over 2. It's going to be 3 pi over 2.
What could you put in that in 1/2?
It can also be negative pi.
Correct. There's a million different ways to describe every single point in polar, because you can go around a million, trillion times, or backwards or forwards. Generally speaking, though, when given the chance, just go counterclockwise once. Go counterclockwise once. So when you graph this, 0, -5 is right there. So it's 5 away, and it goes how far around? 3 pi over 2. 270 degrees. Correct. In A, you're given polar coordinates, and you need to have Cartesian. So try that for me. Do that for me. Make a little triangle, right? I mean, what are you looking at? You're going a distance of 7 and pi over 3. You know, so pi over 3 right here. And what's that distance? 7, right? So you need to actually find this x value and this y value. How do you do that?
Good old sign. Yes.
Yeah, so you know that sine of pi over 3 is going to be
X over
y over 7. And you know that cosine of pi over 3 is going to be x over 7. What does this tell you? It tells you that y is equal to 7 sine of pi over 3, and x is equal to 7 cosine of pi over 3. What is sine of pi over 3?
7 times.
It is not. Answer the question I asked. What is sine of pi over 3?
No, 1 square root of
What is sine of pi over
1
3?
over square root of no 2
Root 3 over 2 for the win! Root 3 over 2. Good job. And what's cosine of pi over 3? 1/2. So that's where they come from, everybody. That's where they come from. So you're using, again, basic trig values. Of these two, well, it gets a little easier on these. 5 pi. 5 pi. So you go, what point is that?
That's
What point is that in Cartesian
that's
land?
on
Henry.
X section.
It's negative 5, 0.
Correct. And what about Q? Which one is that?
5, 0.
5, 0. Oh, look, are some of them the same? Yeah, any point on the x-axis is going to be the same because it is its distance and it has no angle value. Well, its angle value is 0. There's Cartesian graph paper, but also what kind of graph paper can you have? Polar graph paper, absolutely. And so instead of a grid, you're going to see concentric circles. So here is some polar graph paper and 1 point plotted on it. There's some polar graph paper right there, the point P, right there. What is the R value for P? And what's the angle value? Yeah, it's as easy as reading a Cartesian graph. It is where it is. You find out what cross sections it's hitting, and you are done. Nice. And you absolutely can generate and get Cartesian graph paper. It's a good time. Okay, so what do these start looking like? Well, you can make some really pretty shapes. Really aesthetically pleasing shapes. You're looking at rotational graphs. Okay, so for A, it's the form of the circle of radius 1 around the origin.
X squared plus y squared equals 1.
That's relatively straightforward. You've thought of that as relatively straightforward, but what's even more straightforward than x squared plus y squared equals 1? R equals 1. That's pretty ridiculously straightforward. So it simplifies shapes that have some sort of rotational dimension to them. Symmetry across multiple direct variation lines. Here's the fun question, though. We have this right here in Cartesian. What do I want it in? Polar. You have 30 seconds. Tell me what the polar equation is. You know that, what was sine of theta equal to? Here's your point right here. It was r theta, right? This was y and this was x. What was sine of theta?
Radius.
Sine is opposite.
R over
So opposite is, here's theta.
Y over
Y over what?
R.
R. So what does y equal? Go with it. What does y equal?
R sines.
R sine theta. In this graph right here, what did y always equal? This one right here. What did y always equal?
1.
1. So you have 1 is equal to r sine theta. So what does r equal?
1 over sine.
1 over sine theta. You now have a function that relates r and sine. You now have a function that relates r and sine and only gives you the horizontal line y equals 1. Y is equal to r sine theta. Similarly, what does x equal? Come on. R cosine theta. Exactly. It is a sinusoid, but can you tell me the method you would use? Jesse, graphing. Okay, one is graphing, absolutely. So how would you graph it?
Table of values.
Table of values. So you could make a table of values. Is that possible on something like this?
Yes.
Absolutely. You can plot points. What else could you do? What'd you say? Calculator. Take out your calculators and graph A for me right now. Do that right now. Record, and we do zoom 6. Is that pretty? It's kind of cool. Let's get petals. It's a flower. It's very nice. What's interesting about that is, do you see an infinite number of petals? No. So as this function goes on, as you get more and more theta values in there, it overlaps itself. How often, so where does it start? If we had time equals 0 on this thing, where does it start? What point is it at? At time equals 0, where is it?
7.
It's at the what?
7.
Yeah, what is sine of 0? 0. So it starts at the origin, and then it travels along this flowered path. When does it get back to, how long does it take for it to get back to the origin? How long does it take for it to get back to the origin?
Pi.
Pi over 2, because you're multiplying it by 2. It's 2 theta, right? So each of these petals, what happens? That is 0 to what? Pi over 2. This petal is what? Pi over 2 to what?
Pi.
To pi. This one is
Pi to pi.
pi to 3 pi over 2. Yep. And what's this one? To 2 pi. It's very cool. So for example, well, not for example, is this something you're going to pay very careful attention to? Yes. Where does it get back to where it started? You're looking for symmetries. That's going to be a huge thing, especially, for example, when we talk about finding areas inside polar. Do you need to integrate across from 0 to 2 pi on this? If I told you how to find the area of one of the petals, do you have to find all 4 of them?
No.
You just find 1 and multiply by
4.
double symmetry. Very cool. Yes. The equation at the top is what we're going to use to find areas underneath polar curves. Areas underneath polar curves. First question for you is, how many degrees in radians is it around a circle? 2 pi. So this shaded region right here, this shaded region, what percent of the circle is it? Theta over what? 2 pi. So this right here is some part of the circle. How much of it? Theta over 2 pi. What is that? What's that right there? Area of the whole what? Whole circle. So when you simplify this, what do you end up with? 1/2 r squared theta, which is the area of the what? Of the sector. So that would be a perfect answer only if you had a circle. Only if you had a circle. Okay, well, let's go back to fun integral land. You had a function, and you broke out. How did you find this integral? You had an infinite number of what? Yeah, these little things, right? And whatever, right? I'm doing this really sloppy. But the point is, did any one piece or any one of these perfectly accurate? No. How did we make this perfectly accurate? We ended up chopping it into how many pieces? An infinite number, right? We took a Riemann sum, and then we found that tie between Riemann sums and integral land. Same exact thing here, but instead of adding together rectangles, what are we adding together? Little tiny slices. Triangles. It's not really a triangle because there's a curved base to it. There's a curved base to it. So we're taking infinitesimally small slices, but instead of taking rectangles in this case in polar land are sectors. They are sectors. Functionally, is it identical essentially to how you integrated before? Absolutely. You have a lower bound of integration and you have an upper bound of integration, and you have instead some function that is in terms of r. You have something that's in terms of r. Okay, so what does that mean? I like the name of this. See what it's called? Liebeston. Yeah, there's a little accent right there. Or that's just a speck on. Nope, not a speck. Here it is right here. If I asked you right now, we've only touched on this for 5 seconds. If I asked you to write the integral that represents the area of that shape, do it for me. Write something down that you think represents the area of that shape. You have 10 seconds. 10? Do you have an integral they'd like to share? What do you got? Integral of what?
From 0 to 2 pi.
Of what?
Of 3 plus 2 cosine theta.
3 plus what? 2 cosine theta, yeah?
D theta.
Close. There's a lot more in it, though. What is he missing?
1/2.
What? Yeah, what goes out front? You can always factor out the 1/2. What else do you have to do? Squared. Correct. Is there something else missing? What else is missing? There's something missing, kids. Calculator. The integral from what to what?
4 pi to 0.
4 times the integral from 0 to what? Pi over. How many petals are there?
4.
So do you need to integrate across all 4 of them? You could if you wanted to, but you don't have to. You could do one of them, so it's going to 4 times 0 to what? Pi over 2. It tells you right here. It tells you one of the petals is 0 to pi. We already determined that earlier, right, James? Because how many petals are there?
But it's 2.
Why is it?
Just
Wait.
half.
No, it's 2 because
I'm not done writing it in yet, okay? I haven't gotten to the actual formula. So then, what is that formula? 1/2 r squared d theta, right? What is r in this case? 3 sine 2 theta squared d theta. So yes, it becomes 2 times 0 to pi over 2 of, actually, what else can you put out there? So it's 18, right? Because it's the 2, what's 3 squared times 2? Sine squared, actually I'll just write it out because I don't like writing both of them. 2 theta squared d theta, like that. What does that come out to be, Matt?
Plug in 100.
Oh, let's pause here for
14.137.
14 point what?
1372.
1372?
1372.
I just wanted 3, yeah. It is really, really important that you can do that on your calculator, kids, because what essentially you need? Yeah, so look, you have r. Where can you plug that in? So what does y equal? What does it equal? 3 sine 2 theta times sine theta, and x is equal to? Not sine theta, yeah, exactly. It is disgusting. Didn't I say that I was going to be terrible? Now here's the thing. You now have x in terms of theta, and you have y in terms of theta. Can you find d theta, dx d theta, and dy d theta? Yes and yes. What does it look like? It's going to be terrible. Are you ever going to do that by hand? No. But should you be able to write the integral? Yeah. Is this absolutely something they could ask you like on a multiple choice question? I already asked you some of those on the last test, but with parametric. There's not that much difference here. There's not that much difference. So I guess if you walked away with one thing, actually 2 things today, walk away with this and walk away with 1/2 r squared theta. Those are probably the 2 things you want to walk away with today. Absolutely. Okay, you have all your tablets out. You guys have a relative